Hello, myself Navneet Jain. I am lecturing in electrical engineering. I teach subject circuit analysis for electronics second year student here Government RC Kitan Polytechnic College. Today I will deliver lecture on mutual inductance. Let's see. What is mutual inductance? I am defining here mutual inductance between the two coils is defined as the property of the coil due to which it opposes the change of current in the other coil, or you can say in the neighboring coil. When the current in the neighboring coil changes, the flux sets up in the coil, and because of this changing flux, EMF is induced in the coil called mutually inductance induced EMF, and the phenomenon is called as mutual inductance. Here I explain how it works. Two coils, namely coil A and coil B, are placed nearer to each other, as shown in this adjacent figure. When the switch S is closed and the current flows in the coil, it sets up the flux phi in the coil A, and EMF is induced in the coil, and if the value of the current is changed by varying the value of resistance R, the flux linking with the coil B also changes because of this changing current. Thus this phenomenon of the linking flux of the coil A with the other coil B is called mutual inductance. For determining the mutual inductance between the two coils, the following expression is used: Em equal to M di1 by dt, or M equal to Em upon di1 by dt. This is equation 1. The best example of the mutual inductance is the transformer, which works on the principle of Faraday's law of electromagnetic induction. A coefficient of coupling, the fraction of magnetic flux produced by the current in one coil that links with the other coil, is called the coefficient of coupling between the two coils. It is denoted by two coils are taken, coil A and coil B. The figure is shown here. When current flows through one coil, it produces flux. The whole flux may not link with the other coil coupled, and this is because of leakage flux by a fraction K, known as coefficient of coupling. Here K equal to 1. If K equal to 1, when the flux produced by one coil completely links with the other coil and is called magnetically tightly coupled. If K equal to 0 is when the flux produced by one coil does not link at all with the other coil, and thus the coils are said to be magnetically isolated. Next, dot convention. Dot convention is a technique which gives the details of voltage polarity at the dotted terminal. This information is useful while writing KVL equations. If the current enters at the dotted terminal of one coil or inductor, then it induces a voltage at another coil or inductor which is having positive polarity at the dotted terminal. Next, if the current leaves from the dotted terminal of one coil or inductor, then it induces a voltage at another coil or inductor which is having negative polarity at the dotted terminal. Consider the following electric circuit which is having two inductors that are connected in series. It is shown in this figure. Since the two inductors are connected in series, the same current I flow through both inductors having self-inductances L1 and L2. In this case, the current I enter at the dotted terminal of each inductor. Hence, the induced voltage in each inductor will be having positive polarity at the dotted terminal due to the current flowing in another coil. Apply KVL around the loop of the above electric circuit or network. Now we apply here KVL. we get V minus L1 di by dt minus M di by dt minus L2 di by dt minus M di by dt equal to 0 according to KVL. Now separating it, we get V equal to L1 di by dt plus L2 di by dt plus 2M di by dt. We get finally V equal to L1 plus L2 plus 2M into di by dt. The above equation is in the form of V equal to L equivalent di by dt. Next, therefore, the equivalent inductance of series combination of inductors shown in the above figure is L equivalent equal to L1 plus L2 plus 2M. In this case, the equivalent inductance has been increased by 2M. Hence, the above electric circuit is an example of electric coupling which is of heating type. Now, coupling of opposite type, consider the following electric circuit which is having two inductors that are connected in series. In the above circuit, the current I enters at the dotted terminal of the inductor having an inductance of L1. Hence, it induces a voltage in the other inductor having an inductance of L2. So, positive polarity of the induced voltage is present at the dotted terminal of this inductor. In the above circuit, the current I leaves from the dotted terminal of the inductor having an inductance of L2. Hence, it induces a voltage in the other inductor having an inductance of L1. So, negative polarity of the induced voltage is present at the dotted terminal of this inductor. Again, we apply KVL around the loop of the above electric circuit or network. We get V minus L1 di by dt plus M di by dt minus L2 di by dt plus M di by dt equal to 0 according to KVL. Now, by separating, we get V equal to L1 di by dt plus L2 di by dt minus 2M di by dt. We get finally V equal to L1 plus L2 minus 2M into di by dt. The above equation is in the form of V equal to L equivalent di by dt. Therefore, the equivalent inductance of series combination of inductors shown in the above figure is equivalent equal to L1 plus L2 minus 2M. In this case, the equivalent inductance has been decreased by 2M. Hence, the above electric circuit is an example of electric coupling which is of opposing type. Yes, this is the end of this topic. Thanks.